So there was a question about how volume change ratios are represented in linearized elasticity. So here's how it's done. Okay, so okay, so recall that the proper volume change is determinant of f. Okay? Now we can expand this, right, in a Taylor series. The first order, the zeroth order term is 1. The first order term turns out to be trace of f, and you can try this out. Okay? And then there are higher order terms, there are quadratic terms in the displacement gradient. And there are cubic terms. Okay? Since we're working with linearized elasticity, what is done is to keep only the first order terms, zeroth and first order terms. Okay? So on the right hand side, we have the linearized volume change ratio for linearized elasticity. And you observe that, okay, first let me state that. So this is the volume change ratio in linearized elasticity. Okay, and actually let's just write this out. Which what this term turns out to be is 1 plus partial of ui with respect to, well, in order to make this work, let me write it as this. Okay? All right, where the sum is implied. Okay? But then you recognize that this term is what in linearized elasticity is also called the volume strain or the volumetric strain. Right? And in fact, it is equal to the trace of epsilon. Okay? I'm sure you've all seen the volumetric strain as being written as equal to trace of epsilon in linearized elasticity. That's where it comes from. Okay, so that's how volume changes are approximated in linearized elasticity.